So welcome back to Chemical Engineering Thermodynamics 1. We're now at Unit 2. Now Unit 2 is a very interesting topic and I really want you guys to do the groundwork and watch the preliminary videos and go through the supplementary material before starting to watch this video. Now let's look at what we're going to be expecting to cover in Unit 2. So Unit 2 deals with the second law of thermodynamics. We're going to be able to describe thermal systems and system relationships, calculate the entropy for open systems. We're going to relate the second law to heat engines. We're also going to examine the third law as well as the zeroth law of thermodynamics. Now let's start by looking at reversible and irreversible processes. So the second law basically provides a way for us to determine if a process is reversible or if it's irreversible. Now, when we're looking at reversibilities, if the entropy generation is positive, then the process is irreversible. If the entropy generation is zero, then our process is reversible. And of course, if it's negative, then this process cannot occur as previously described. Now, entropy is a pretty new term for you. So let's first give you a bit of background on reversible and irreversible processes, and then we'll go into what entropy is all about. The reversible process is an idealized process, meaning it's basically the standard that we use as a representation of what the ideal situation would be like. So this process can basically be reversed without leaving a trace on the surroundings. So hence, at the end of the process, both the system and surroundings, they're able to go back to their original state. So in other words, a reversible process does not occur in nature. However, it basically serves as a theoretical limit for the corresponding irreversible ones. So in other words, they can be approximated but never really achieved. So why should we even bother to look at this kind of process if it's really and truly not going to occur? One is because we can easily analyze these systems, right? By looking at the series of equilibrium states during these reversible processes. Another reason is because they would now serve as an ideal model. So we can compare actual processes to see how they actually behave in real life. Now, a special type of closed system is called reversible. So in other words, a process is reversible if its direction can be reversed at any point by a small change in conditions, meaning it can go back to its original state just by merely changing something in its initial conditions. So if we have a piston cylinder setup and it's operated to cause an expansion or compression of a gas, so we can assume perfect insulation. So once we have perfect insulation, there is no heat. So remember those series of definitions that I asked you guys to look up? So that means our system is adiabatic. So imagine now that we put small weights on top of our piston and they have the mass m. So let's observe this system. So if you look at the top right or above, you'll see a piston setup, right? So it's basically in an evacuated space, it's frictionless, and it's free from any dissipative effects. And of course, you see the weights of mass m on the top. So the initial state in equilibrium with the upward force of the gas is on the piston. So in other words, there's the gas in the piston and it's there's an upward force that is acting on the piston itself. So if we were supposed to gradually remove the weights from the piston, it's going to cause it to rise and to gradually oscillate. So imagine that we are removing very small amount, very incremental masses, and it's going to cause a continuous steady rise of our piston. So imagine now we replace this mass, remember the mass M that's on top of the piston, we replace it with a pile of powder blown in a fine stream, right? So imagine that. So we're going to now reverse the transfer of the powder. So in other words, the reversible process is never completely realized and a mere idealization. So imagine we keep removing small amounts of this powder. It's going to rise steadily, right? So the idealization is basically useful for engineering calculations. Real processes that occur, they are not reversible. And basically irreversibilities reduce the efficiencies of processes because for one, they can never go back to their original state. And there's always something that's happening within the system that's going to cause it to have a reduced efficiency. So let's look at reversibility as it relates to a chemical reaction, right? So we have calcium carbonate decomposition in a constant temperature bath as shown above, and our equilibrium is reached at a given temperature and pressure of carbon dioxide to basically balance out the weight that is on top. So we have a similar piston arrangement. Inside we have the calcium carbonate decomposition, and when it decomposes we are going to be forming calcium carbonate as well as CO2, and then that pressure based on the reaction that's going on is basically enough to balance the weight that is on top of our piston arrangement. So based on this chemical reaction, right, any change in the system can cause the equilibrium to go in any particular direction. So for example, if the weight is increased, then that will basically raise the pressure. So more CO2 will combine with the calcium oxide to form more calcium carbonate, and therefore the frictionless piston will fall. So if we also change the temperature, we will also have a similar effect. So let's look at other examples of reversible processes. So we can have the extension of springs, slow adiabatic compression or expansion of gases, electrolysis with no resistance in the electrolyte, as well as the frictionless motion of solids, in addition to the slow isothermal compression or expansion of gases. So I want you guys to just go ahead and do additional reading on these examples of reversible processes so that we can discuss them further in our seminar session. So now let's take a look at the real world. So our system and surroundings cannot return to their original state conditions if the process is reversed, right? So let's look at a very simple example. So we have an egg and we're gonna fry this egg for breakfast, right? So the first reaction, which is to fry our egg, is possible, right? So crack the egg in the oil, we get our nice sunny side up, right? Now, if I want to, let's say, go back to my initial condition to get back my whole egg, not so much. That's virtually impossible. So this is basically the simplest way of expressing what an irreversible real life process is like. So let's examine another situation. So imagine we have an automobile engine as we see on the left, and it has traveled, let's say, a distance with the aid of a fuel, which is equal to the amount X. Now during this process, the fuel is used to provide the energy to the engine, which would then basically convert itself into heat energy. And of course, we'll have some smoke being given off. Now, at the end of the day, what makes it irreversible is that we are unable to retrieve the energy that is lost by the fuel. So we cannot get it back in the original form. So hence, it is irreversible, and it is a real life process. So here are some examples of other irreversible processes. So remember that an irreversible process means that both the system and the surrounding are unable to go back to their original state once the process is reversed. So let's look at the relative motion with friction. There's also throttling, heat transfer, diffusion, as well as electricity flow through a resistance. So as usual, I need you to go and read up on all these so that we can have a discussion if there are any challenges in our seminar session. So we have examined reversible processes as well as the irreversible processes. Now, how does this relate to the second law of thermodynamics? Now, what does the second law of thermodynamics say? The thing is that we already know the second law of thermodynamics without even realizing it. So this is what it says. The second law of thermodynamics states that the heat cannot transfer from one body at a lower temperature to a body at a higher temperature without the addition of some energy. So that's just like running your AC. It's gonna cost you because we're transferring it at a lower temperature. So this is why when you run your AC for a long period, like what I did in the summer, it's gonna cost you a lot of money. So we've come to the end of this lecture. So we've just basically touched the surface to introduce the second law of thermodynamics. So of course, I need you guys to, as usual, review the lecture content and of course, complete the tutorial so that we can have a fruitful discussion in our seminar session. So these are some of the things you need to do for your individual work. Write down and familiarize yourselves with the equations as well as the definitions of key concepts. I need you to also work through the tutorial questions for discussion, review the supplemental notes, and also watch the supplemental videos and read the chapters for the unit. Next lecture, we will also be looking at the term that we introduced, which was entropy, and further develop on the second law of thermodynamics. Thank you.